what's up guys? It's the Log Ride Legends here, back with another video. Alright, so today we're going to be riding the log ride at Knott's Berry Farm. And we're going to be
talking about the physics. Now, the first ramp up. As the conveyor belt lifts us up to the top of the hill, static frictional force between the rubber of the conveyor belt and the rough galvanized steel bottom of the log keeps the log moving upward with the belt. The log ride uses several mechanisms to both propel us up the hill and make sure that we don't slide backwards and hit the logs behind us. Firstly, the rubber conveyor belt, powered by motors, carries the log at a constant velocity up the incline, whilst the strawberry kiwi yellow pegs on the right side hold the log in place with respect to the conveyor belt so that the log doesn't backslide. The pegs are equally spaced apart so that if one breaks, another peg will be there to stop the falling log.
Yeah, I'm the boss.
As the log enters the water, we can now consider it a mass that has entered a resistive fluid. By using this one equation, we can determine values for both the log and the water. If you want to solve for the density of the liquid, this is how you would rearrange the equation. Likewise, this is how you would solve the equation for A, the frontal area of the log, CD, the coefficient of drag, and V, the speed of the log.
Hey, Hicks, do you mind if Ow!
Alright, now I'm going to introduce you to my colleague and very vague acquaintance, Hon Tran, to talk to you about Archimedes' principle.
Shut up, Hanjo. Well, you know, it's about buoyancy and how stuff floats. Basically, the force of buoyancy that keeps the log afloat is equal to the weight of the water displaced by the log.
The flowing water propels the log through the majority of the ride. As soon as we were dropped from the conveyor belt into the water, we noticed that water was being pumped from a location under the conveyor belt onto the track. As it turns out, water is pumped from the bottom of the ride and circulates up the initial ramp through a system of hidden pipes to reuse the water for the next rotation of logs. Everybody knows that the reason why we stay on the course during the winding sections of the track is because the normal force of the sides of the track counteract the log's centrifugal or outward force. Centrifugal.
No.
To anyone watching this, I recommend searching the comments for comments by Trevor Strickland. He brings up every good points.
Centripetal force, or the force that keeps objects moving in a circular path by pulling the object towards the center, is the reason why the log doesn't veer off course and lead us to certain death. In this case, the centripetal force acting on the log flume consists of the normal force of the half-pipe shaped track. There are two ways to calculate centripetal force. Firstly, you can use this equation, or you could just use the sum of the forces acting on the object. As the belt lifts us up the ramp, our gravitational potential energy increases because our height increases. There's a direct relationship between an object's height and its gravitational potential energy. When the log reaches the peak of the incline, its kinetic energy has a value of 0 because the log is not in motion. However, when the log begins its descent, the gravitational potential energy begins to convert into kinetic energy, and by the time it reaches the bottom, almost all of its gravitational potential energy has turned into kinetic energy. The energy that is not converted into kinetic energy is released from the system due to friction with the air and water. When the log comes to a stop at the bottom of the ramp, momentum is conserved, shown by us lurching forward in our seats. We lurch forward because even though the log stops, our momentum, and therefore our velocity, is still conserved until we push off of the log or fall through the front of the log. This incline uses the same design as the initial ramp, with the conveyor belt and the pegs for support. Since the log has a large frontal surface area, the frictional force from the water and the air causes the log to slow rapidly. The staff member then stops the log at the very end. In summary, these are the concepts we thoroughly and astutely analyzed and brought to you, the struggling survivors of AP Physics C. May you all rest in peace.
Hey guys, thanks for watching the last episode of Log Ride Legends. Don't forget to like, comment, and subscribe. This is the Log Ride Legends. The gang's all here. It's just me and little Sparkles here. Sparkles, say meow. Hey, Sparkles, come on, say meow. Say meow. Well, that's okay. She's a cutie. Anyways, hey.